In part 6 of section 16, we're going to discuss slant asymptotes. Theorem 16.2 says, let f of x equal p of x over q of x be the equation of a rational function. And we know that with a rational function, by definition, we have to have a polynomial as the numerator, and we have to have a polynomial for the denominator. And each one of those polynomials will have a degree associated with it. If the degree of the numerator minus the degree of the denominator is exactly equal to 1, then that means that your function will have a slant asymptote. This is also known as an oblique asymptote. Now the implication here is that if the degree of the numerator minus the degree of the denominator is equal to a positive 1, then that means that f has to be top-heavy. And one of the implications of it being top-heavy is that there is no horizontal asymptote. And that was back when we discussed the horizontal asymptote concept. So what I also mentioned back in the horizontal asymptote discussion was that if it's top-heavy, yes, there is no horizontal asymptote, but there might be a slant asymptote. So this theorem gives us the criteria to check to see whether or not there is going to be a slant asymptote. Now, of course, this begs the question, how do you find the slant asymptote if you know there's supposed to be one? So that's where the division algorithm is going to come in. So you're going to perform the division process, and then the line y equals the quotient is going to end up representing your slant asymptote. So you're going to apply the division algorithm to f. So make sure I specify that. You're going to apply it directly to f because f is already going to be a rational function. So example 16.11 is going to give us an opportunity to be able to practice this. It says the equation of several functions is given. Find the slant asymptote of each function. And we have here a top-heavy rational function. And I'll notice that the degree of the numerator is 2. The degree of the denominator is exactly 1. So this fits the condition that the degree of the top is exactly 1 higher than the degree of the bottom. So I'm going to perform the division process with this. And since it's a rational function, it's already set up to where I have a dividend and a divisor. I don't have to go searching for those things. It's already here. And because of the divisor being x minus 1, I can go ahead and use synthetic division, setting up my dividend with the coefficients 1, negative 1, negative 1, bring down the lead coefficient, and then I'm going to use positive 1 to represent the divisor. Now I'll go through the multiply and add steps, 1, 0, 0, and then negative 1. That last value we write represents the remainder. Everything to the left of this now represents the quotient. And that's the part of this whole process that we're interested in, is the quotient. So the slant asymptote is going to be located at y equals x. X represents the quotient, and then we just put a y equals with it, and that's how we get the equation. Let's try this for part B. We have another functions equation given, and it is f of x equals x cubed plus 1 divided by x squared plus 2x. Again, this is top-heavy, and not only is it top-heavy, it is top-heavy by exactly 1 degree, with the degree of the top being 3, the degree of the bottom being 2. There's a difference of just 1. So with that, I want to go ahead and apply my division algorithm, and because of the divisor being x squared plus 2x, I'm not going to be able to get away with using synthetic division here. So we are going to have to use long division, and for long division I have a dividend of x cubed plus 0x squared plus 0x plus 1, and my divisor is going to be x squared plus 2x plus 0. And I want to create a little section for scratch work. And this will help me to start the first round of the division process. So everything's set up now. Let's take x cubed from the dividend and let's divide it by x squared from the divisor. And that's going to result in x. So I'll put x up here above the 0x, multiply x through to the divisor. I'll write that down underneath my dividend, x cubed plus 2x squared plus 0x, and that becomes the quantity that I want to subtract from my dividend. The x cubes will cancel. 0x squared minus 2x squared will be negative 2x squared. 0 minus 0 can still just be 0, and then we'll bring down the plus 1, completing the first round. Let's do it one more time. This time let's take negative 2x squared and divide it by x squared to get negative 2. So x minus 2 ends up being the quotient. And then I'm going to write here stop. Because you have to be aware of what you're using the different tools for. We have used division for a number of things. Well, for starters, to do division. Secondly, we've been using it for the remainder theorem. Then we used it for the factor theorem. And now we're using it for finding a slant asymptote. And the only part of this whole division process that we really care about is the quotient. I don't need the remainder. That's something that I need for the factor theorem. That's not what I'm doing here. So all I need is to now write down that the slant asymptote is at y equals x minus 2. And that gives me the slant asymptote for this function.